A secure multi-party protocol has many properties like correctness, privacy of inputs, etc. Fairness is another intuitive property which we would like protocols to have. If a protocol is fair, then an adversary cannot prevent the honest parties from obtaining the output of the computation if he also obtains it. This is modeled by having an ideal world where the functionality gives output to all the parties or to none of them. In this work, we focus on finite two-party functionalities. A functionality is finite if its input and output size do not depend on the security parameter. There's a lot of interest in the problem of fairness. However, the understanding of some of the most fundamental primitives is still lacking. In this work, we are going to study the relationship between primitives such as fair exchange, fair coin flipping, and fair random oblivious transfer. And we ask questions of the following form. Given access to a fair primitive, can we realize another primitive fairly? Let us take a look at the functionalities we'll be dealing with. First, we have functionalities that take input. For example, the exchange functionality, which takes two inputs x and y, gives Alice's input to Bob and Bob's input to Alice. Then we have sampling functionalities, which do not take input, like the coin functionality, which flips a coin and gives the outcome to both Alice and Bob. We also have the randomized oblivious transfer functionality, which picks 3 bits at random, gives x0, x1 to Alice, and c and xc to Bob. More generally, we have a sampling functionality fxy, which picks a sample AB from a joint distribution xy, gives A to Alice and B to Bob. We call this a sampling functionality over the joint distribution xy. Let us take a look at the results we have. If we look at the landscape of fairness, at the bottom we have functionalities which have fair protocols. This might be under computational assumptions or with access to an unfair functionality. We know that coin does not have a fair protocol. This follows from the result of Cleve in 1986. We also know that if we have exchange functionality, then we can obtain a fair protocol for coin. That means exchange also does not have a fair protocol. Our first result shows that even with access to coin, one cannot obtain a fair protocol for exchange. We then study the randomized oblivious transfer functionality and show that it too does not have a fair protocol. In fact, our result is more general, and it shows that any sampling functionality over a distribution that is non-trivial does not have a fair protocol. Our next result shows that with access to the randomized oblivious transfer, one cannot get a fair protocol for coin. Once again, our result is more general, and any sampling functionality with something called zero common information cannot give coin. We'll come back to this later. Finally, we have a positive result, which shows that given access to coin, one can obtain a fair protocol for randomized oblivious transfer. In this talk, we'll be spending some time on this result and this one. But before moving forward, let us take at some of the related work in this area. The first major result was by Cleve in 1986, who showed that there's no efficient protocol for fair coin flipping. And he gave a very simple fail-stop attack, which works irrespective of any computational assumptions that we may make. And this led to the belief that any functionality that is non-trivial probably does not have a fair protocol. However, things changed in 2008 when Gordon et al. Showed that many functionalities of interest, like AND, or Yau's millennial problem, they do have a fair protocol. And this led to a flurry of results in the following years. These results show us that the landscape of fairness is much more complicated than that of unfair computation. In particular, there is no finite complete function for fairness. Coming back to our results, let us spend some time on this one. We are going to show that given access to a coin functionality, one cannot obtain a fair protocol for exchange. For our purposes, it does not matter whether we consider the exchange functionality or the XOR functionality. But even before that, let us see how the Cleave's proof works. Recall the coin functionality. The functionality flips a coin and gives the outcome to both Alice and Bob. And if a protocol has to realize this functionality fairly, then it must satisfy two properties: agreement, that Alice and Bob output the same bit, and entropy, that honest party outputs a random bit. Now consider a protocol between Alice and Bob. Say Alice sends the first message, M0. If Bob does not receive this message, then Bob outputs Y0. Then Bob sends a message, M1. If Alice does not receive this message, then she outputs X1. This goes on. The ith round looks like this. XR plus 1 and YR are the final outputs of Alice and Bob. Okay. Now, Y0 should be uniformly distributed, because if it is not, then Alice can simply abort and bias the output of Bob. Similarly, X1 should be uniformly distributed. And one can show that all the variables on the left and all the variables on the right, they should be uniformly distributed. Now, we know that Y0 and X1 should be independent of each other because they are computed without any communication between Alice and Bob. This means that the probability that both of them are equal to 1 is 1/4. However, at the end of the protocol, we want that XR plus 1 and YR are the same. This means that the probability that both of them are equal to 1 is half. And we can see that there is a significant difference between 1/4 and 1/2. This means that there exists a round I such that the probability that these two variables are equal to 1 minus the probability that those two variables are equal to 1 is at least 1/R. Now we can see how the adversary can take advantage of this 1/R factor and bias the output of Bob. The adversary corrupts Alice and does the following mental experiment. So it first follows the protocol honestly up to round I minus 1, and in the round I, it does the following mental experiment. If I send the message MA, but Bob does not send the message MB, what is my output XI going to be? Based on the value of XI, Alice can choose to selectively abort. If XI is equal to 0, then Alice would not even send the message MA, and Bob would output YI minus 1. On the other hand, if XI equal to 1, then Alice would send the message MA, Bob would send MB, but then Alice would not send this message, in which case Bob would output YI. One can show that this attack is able to produce a bias of 1/R in Bob's output. And this completes our discussion of Cleave's proof. The important thing to note here is that Alice can compute the value of Xi without sending the message MA for the ith round. Now we come back to our original problem. We want to show that even with access to the coin functionality, one cannot realize XOR fairly. The XOR functionality is simple. Alice and Bob have inputs X and Y, and they get the XOR of their inputs. If we assume that Alice and Bob choose their inputs at random, and any invalid input is substituted by a default one, then we still have the same two properties which we had in the case of coin: agreement and entropy. And because of these two properties, once again, we have the following setup, that the probability that these two variables agree minus the probability that these two variables agree is at least 1 over r. Now once again, the adversary would corrupt Alice and do this mental experiment, that if I send the message MA and I don't get the message MB, what is Xi going to be? But now there is a problem. There's a coin functionality which the parties can access, and the value of Xi can depend on this bit B. Now, in order to find Xi, Alice must send the message MA and get the outcome of the coin. But if she does that, it will be too late for her to force Bob to output Yi minus 1. Now, what does Alice do? Alice can at least find out whether Xi depends on the bit B or not. If it turns out that Xi is independent of the bit B, then we can have the old attack which we had in the case of coin. However, if Xi depends on the bit B, then as I said before, Alice would have to send the message MA and get the outcome of the coin. But then it will be too late for her to force Bob to output Yi minus 1. Now in this case, Alice simply continues the protocol up to the end and forces Bob to output YR. And surprisingly, this works. The reason this works is because since Xi depends on the bit B, this makes it independent of Yi minus 1. And because XOR is a deterministic functionality, once we fix the inputs, the output is also fixed. This makes Xi independent of the final output as well. In simple words, the joint distribution of Xi and Yi minus 1 is similar to the joint distribution of Xi and YR, conditioned on the fact that Xi depends on the bit B. This allows us, so Alice can force Bob to output YR instead of Yi minus 1 and achieve the same effect. So this completes a high-level overview of our proof, and you can see the paper for more details. Let us spend some time on our second result, which shows that with access to the oblivious transfer functionality, one cannot obtain a fair protocol for coin. As I said before, this result is more general, and any distribution with zero common information cannot give us coin. So let us see what common information is. Suppose there are two parties, Alice and Bob. Alice gets a sample from distribution X, and Bob gets a sample from Y. They both output the same value Q. Then the common information between the joint distribution X and Y is the maximum amount of entropy this variable Q can have. For any joint distribution, we can define a bipartite graph where two nodes U and V are connected to each other if and only if the probability of UV is not 0. For example, coin has this graph, and random oblivious transfer has this graph. Note that this graph has only one connected component, and one can show that any joint distribution that leads to a graph with only one connected component has zero common information. On the other hand, coin with two connected components has one bit of common information. And this leads us to our theorem. If a protocol has two phases, such that in phase 1, the parties access OT any number of times as they want, and in phase 2 they communicate for log and rounds, then such a protocol cannot realize the coin functionality. For the purpose of this talk, let us focus on a protocol that has only phase 1. That means the parties do not communicate, they only get samples from randomized oblivious transfer. Before proving our result, we remarked that for such protocols, it was proved by Witzenhausen in 1975 that the above theorem holds. However, we use spectral graph theoretic techniques and obtain slightly sharper results. Once again, recall that for a coin functionality, we have the following two requirements: agreement and entropy. Now, if we have a protocol where parties get only one sample from oblivious transfer, then their joint view looks like this. In order to handle the case of multiple samples, we define a natural notion of graph products. The product graph for multiple samples is a very complicated graph, but it still has only one connected component. Let's say the parties output 0 for these values and 1 for these values. Note that any of these circles cannot cover the entire input because the output of the parties must have some entropy. Now we are interested in finding out the weight of the edges that go across, because this gives us the probability of disagreement. And this is captured by the Cheeger constant. In order to lower bound the Cheeger constant, we lower bound the second eigenvalue of the Laplacian associated with the product graph. And this turns out to be a constant, which shows that no matter how many samples from randomized oblivious transfer is available, the weight on the edges going across is a constant. That means the probability of disagreement between the parties is a constant, and hence we cannot obtain coin. To summarize, we have established several interesting relations between some fundamental primitives, and our results demonstrate that the landscape of fairness is much more complicated, and there's still a lot of work to be done here. Thank you.